Reservoir simulation is ultimately a tool to make accurate, efficient quantification of the uncertainty associated with trying to understand how subsurface fluids way beneath the surface move and get transported as a function of space and time. So it is important to recognize that you need to do the modeling of these complex things like enhanced oil recovery processes, managing subsurface water resources, the management and the design of CO2 sequestration processes. You want to keep in mind that the more you understand about the system, the better the prediction gets. But in the end, the complexity of the problem still means that whatever you make predictions of is not completely certain. And that's because a lot of the information that we have is actually a sparse sampling of the problem. And the idea behind reservoir simulation is to understand the complexity of the scale representation and capture the physics sensitive to the fact that things vary over a very large span of scales. Reservoir simulation is only one piece of a puzzle that should integrate information about stratigraphic modeling, seismic imaging, structural and stratigraphic information, well-logged data, gridding, upscaling, production data information, well planning and configuration, actual measurements of fluid phases, pressure, volume, temperature, enhanced oil recovery, EOS calculations, the physics of fluid flow, phase diagrams. All of that has to be integrated into the reservoir simulator. So what makes life difficult in reservoir simulation? The trend is a further growth in complexity. So as the easy oil has been recovered, we now need to resort to enhanced oil recovery processes. We need to understand infill drilling possibilities. We need to worry about contamination. We need to worry about subsurface CO2 sequestration. So the complexity is growing. Life is getting complicated, but that's a beautiful computational science problem, right? The more complicated the problem is, the more interesting it becomes from a computational perspective. On this list, I can see 50 PhDs, right? In my group and in many other groups on the planet, there's been tens of PhDs on this subject, right? But we only scratch the surface. Unstructured reservoir simulation is not today still commercial practice, unfortunately, in my opinion. So what gets into the way of unstructured grid workflows is that first you have to make sure that you have gridding capabilities of the geocellular model and the reservoir properties. But then you have to have a gridding and an upscaling framework for both the grid and the physics. You have now to discretize the equations we talked about, these conservation laws, and then you have to solve them. Reservoir simulation, as sophisticated as it may sound, ultimately boils down to wrapping everything within a Newton-Raphson iteration. And as we all know, even for one function R as a function of one scalar variable S, if the function has an inflection point, watch out, right? So it's not rocket science. I'm sure you guys have seen this before. I start with a guess. The root I'm looking for is the thing that makes R 0, which is this guy. So I start with an initial guess, S in it. I take a tangent, That takes me to this point. I take another guess, and I am literally oscillating around the inflection point, right? So unless somebody interferes with this process, this is a non-convergent process. The reservoir simulation problem with nonlinear analysis is, fortunately or unfortunately, like this times 1,000,000, right? So the dimensional space you're solving the problem, if you have 1,000,000 cells, is 1,000,000 coupled equations. So you don't want to go in each and every little equation and do this little fix. You need something a little more robust and a little more rigorous in terms of analysis to guide you. Here is a very simple, supposedly simple, two-cell problem. Now, we're going from one function to two, and I'm looking for the solution that would satisfy my equations as a function of the saturation in cell 1 and the saturation in cell 2. So this is now, luckily, still a two-dimensional problem. So I have S1, these are saturations, volume fraction, 0, nothing, 1, fully saturated with that fluid. So S1 goes from 0 to 1. S2 goes from 0 to 1. In this case, I know what the solution is. It's this guy, because I did it by construction. So it's important to combine linear analysis, non-linear solvers, time evolution solvers, in order to advance the scalable aspects of the reservoir simulator so we can solve our big problems. And I will stop here. Thank you.